In this question, we are given that a bottle of milk is taken out of a refrigerator and it is placed in a pan of hot water to be warmed. And the increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius, and t is the number of minutes since the bottle was placed in the pan. And so m satisfies the differential equation, dm over dt equals 1/4 of times 40 minus m. And we are given initial condition that at time t equals 0, the temperature of the milk is 5 degrees Celsius. And it also can be shown that the temperature is less than 40 for all values of t, of time. And so the first question is a slope field for the differential equation is shown to us. And we need to sketch the solution curve through the point 0, 5. So through the point which is already marked here. And so how can we sketch this solution? We can actually have to move along the curve, the slope field. So we are not moving perpendicular to it. We are not moving under some angle. So these are all incorrect answers. But we have to move along those lines. Like they have to be touching the line, the solution curve. So if we look specifically at these lines, they are tangent, they are small tangent line to the solution curve. And this is the answer to part A. For part B, we need to use the line tangent to the graph of m at time equal to 0 to approximate fm of 2, the temperature of the milk at time t equals 2 minutes. And so how can we do that? We first have to calculate the derivative of m with respect to time at t equals 0. And this is equal to, we just plug in m of 0 into the equation, 1/4 of 40 minus m of 0, which is 5, and this is equal to 1/4 of 40 minus 5 equal to 35 over 4. And then note what we are calculating here. We are calculating using the derivative at point 0. We are approximating the value. Let's say this is 2 time t equals 2 minutes. We are approximating this value with this approximation. So really what we are doing is we are calculating the m at time 2 is approximately equal to m at time 0 plus the derivative of m with respect to time at time t equals 0 times 2 minus 0. And so we have all these values, so let's plug them in. We get m of 0 is given to us 5 plus dm over dt at time 0 we just calculated 35 over 4 times 2 minus 0 is 2, and this is equal to 22.5 degrees Celsius. So the answer to the second question, part B, is 22.5 degrees Celsius. For part C, we are asked to write an expression for the second derivative of temperature with respect to time, and then use that derivative to determine whether the approximation from part B was an underestimate or an overestimate for the actual value of m of 2. And so to do that, we need to, let's first calculate the second derivative, and that's d to m over dt squared, and that is the first derivative of the first derivative. And this is equal to the first derivative of 1/4 40 minus m of t. This is equal to derivative first with respect to m is going to give us negative 1/4 times the derivative of m with respect to t. Plugging it in gives us negative 1/4 times 1/4 40 minus m. This is negative 1/16 40 minus m. And remember that one of the conditions in the description of the problem was that m of t is less than 40 for all t's. For all t. Which means that the second derivative here, d2m over dt squared, is less than 0 for all t. Because this expression is always positive, 40 minus m is always positive, and then multiplying by negative 1/16 gives us a negative number. And if the second derivative is negative, that means that the function is concave down. Which means that if this is a graph of the function, and just approximating what we had, this point is 0, 5, and then this is our approximation along this line somehow goes. But then think of this function as concave down. So approximation will be that we received here. This approximation is overestimate. Overestimate of the actual value m of t, m of 2. Let's move on to part D. In this question, we are being asked to use separation of variables to find an expression for m of t. The particular solution to this differential equation with the initial conditions that we were given before, m of 0 equals 5. And so let's do that. Let's separate the variables and solve for m as a function of t. So dm over dt equals 1/4 over 40 minus m. Separating the variables, we divide by 40 minus m and multiply by dt. So we bring m to left-hand side and dt to the right-hand side. We get dm over 40 minus m is equal to 1/4 dt. Then we integrate both sides. We get integral dm 40 minus m equals integral 1/4 dt. And in order to find the integral on the left-hand side, let's do the substitution. 40 minus m equals u. So negative dm equals du, and so dm is equal to negative du. Let's plug this into the integral. We get integral negative du over u equals integral 1/4 dt. Multiply by negative and take the integrals of both sides gives us ln, absolute value of u, equals negative 1/4 t plus a constant. And so instead of u, let's plug back in 40 minus m, we get ln, absolute value 40 minus m equals negative 1/4 t plus c. Let's use initial condition, which is m of 0 equals 5. Plug it into this equation, we get ln of 35 equals -1/4 times 0, which is 0 plus c. So from here, it follows that c is equal to ln of 35. So our relationship here is ln 40 minus m equals -1/4 t plus ln of 35. Raising both sides e to the expression will give us e to this expression, and e to this expression gives us 40 minus m equals e to the -1/4 t plus ln 35. But then, using the property of exponents, this is equal to e to the -1/4t times e to the ln 35. And this is just equal to, this expression is just equal to 35. So overall, we have 40 minus m equals 35 e to the -1/4 t. So the solution, solving for m, adding m to both sides and subtracting 35 e to the -1/4 t gives us m equals 40 minus 35 e to the -1/4 t. And this is the particular solution. Thank you for watching this video, and I will see you in the next video.